So for this system question, right, the total friction in the whole system is 120 newtons. The friction on just the 40 kilogram block is 48 newtons. We want to calculate the acceleration of the 40 kilogram block as well as the tension in rope B, which is the rope connecting the 40 to the 60 kilogram mass. So it is basically just like the one we did the other day. Okay, let's see if we can remember how that one worked. Okay, let's have a look at this one. First thing we have to remember is that this is a system, and all parts of the system have the same what? They have the same acceleration. Okay, can I calculate the net force on the system to start with? Yes, I can. Okay, I can because I know there's 150 newtons pulling forward on the system, and there's 120 newtons of total friction acting on the system going backward, right? So the F net on the entire system, okay, so I'm going to write F net S there, okay, is going to be 150 minus 120, or plus negative 120, whichever. Okay, in either way, the net force is positive 30 newtons, okay, or 30 newtons forward. That's the net force on the whole system. Now I can calculate the acceleration of the system and each individual part, okay, by taking the net force, 30 newtons, and dividing it by the mass of the system, which is 100 kilograms. So we get 0.3 meters per second squared as the acceleration of the system. All right, now we go back to all parts of the system have the same acceleration. So now I know the acceleration of the 40 kilogram block and the 60 kilogram block. Everybody with me so far? They both accelerate at 0.3. So now what I want to do is break this up. Okay, I can solve for that tension in the in cable B, right, with either box. It doesn't really matter. All right, so I already calculated the acceleration of the 40 kilogram block, 0.3 meters per second, okay, because it's the acceleration of the system. So that part's done. Now to calculate the tension in B using the 40 kilogram block, okay, I'll have the 40 kilogram block. Oh, give me a letter. Sorry, I locked the door. What I have is 150 newtons forward, and I have friction, which they told me on the 40 kilogram block is 48 newtons. And then I have what else acting on the 40 kilogram block? Yeah, the tension in the rope. Okay, that thing I'm supposed to find. Okay, the tension in cable B. That's what I'm supposed to find. All right, so now I know those forces, and what can I calculate about this block, since I know its mass and acceleration? It's net force. All right, so the net force on the 40 kilogram block is going to be 40 times 0.3. Okay, so 12 newtons is my net force forwards. Okay, so 12 newtons is my net force, and net force is the vector sum of all forces. That will mean the tension in B plus the friction, force of friction, which I know is 48, okay, plus the applied force, which I know is 150. Okay, so now that I have that, okay, I'm going to solve for the tension in B by going F net minus the force of friction, okay, minus the applied force, and here's where vectors are important. Okay, this was positive 12 newtons minus negative 48 newtons because the friction was backwards, minus positive 150 newtons. That will give me the tension in that cable or that rope or whatever it happens to be. All right, so we will have 12 minus negative 48 minus 150. So the tension in that cable is 90 newtons backwards. Okay, so that's with the 40 kilogram block.
Can you show us if we can solve for the acceleration?
You can't. You don't have enough information on the 40 kilogram block to do that because we don't know what the tension is in B. Right, so I had to calculate the acceleration of the 40 kilogram block with the system. That's usually the way it works. Okay, usually you have to find the system and then apply it. I mean, there could be situations where you have a lot of information about one piece, you find that and apply it to the system or all parts of the system, but okay, in this case, no.
For your question
Again, I would say I would accept both, because the way I wrote this, in my mind, I was saying this is a force acting on the 40 kilogram block. In that case, it's backwards, right? If it's just the tension, then it doesn't have a vector because it's how tight the rope is, right? But if in this case, because it's from the perspective of the 40, I wrote 90. I would accept it either way. Yeah. Okay. So for the 60 kilogram block, all right, what we know is that there are two forces: the tension in cable B and the force of friction. Okay, we know there's 120 newtons of total friction, and 48 of them were on this block. Okay, so that means we have 72 newtons. Is that right? Yeah, 72 newtons of friction on the 60 kilogram block. All right, so I'm going to calculate the net force of the 60 kilogram block by going 60 times 0.3, which should be 20. Is that right? 18? Exactly? Newtons? Yeah, okay. 18 newtons. All right, and then now I can use that to calculate the tension in cable B using sum of all forces. So it'll be B plus the force of friction. Okay, so B will be F net minus the force of friction. Okay, and that'll be 18 minus negative 72, okay, which is again going to give us 90 newtons, this time in a forward direction from the 60 kilogram block's point of view. All right, so same answer regardless of which block I use because it's a tensional force between the two. Okay. Ringing a bell from the other day? Okay, but again, guys, like there was no difficult math in there, right? It was just how do I get to the math? Okay, we really got to be able to see into a problem when we read it. Okay, we did one like this yesterday. It's a static condition question. All right, this light is being supported by two cables. The cables are identical. They are held at identical angles from the two anchor points. And the mass of the light, or whatever it is 120 kilograms. I want you to find the tension in the cables, okay, or in each cable. Okay, the tension in each cable, or the tension in cable A, because it'll be the same as B. Okay, give you a few minutes on that one. This is not only static, but it's also got some vector analysis in it. All right, so walking around, what I'm seeing on people's papers is very encouraging, okay? And a number of people have got it right, okay? And then a number of people have one small thing that they just didn't realize but had everything else right. So that's really encouraging, okay? The first thing that most people realized was that this is two separate cables. And so they immediately divided this thing into two parts and said that each one had an angle of 50 degrees. All right, that's a good realization and important. Okay, the second thing that most people had was that this thing's 120 kilograms, so that was 1177.2 newtons in terms of gravitational force pulling downwards. Also good. Okay, we're getting that visualization going on here, which is good. Here's the place where people had everything right except one thing. They correctly said that there has to be an upward force that balances this 1177.2 newtons. Okay, but remember that there are two cables. Each one of them is holding how much of that 1177 newtons? Half of it. Okay, if each cable was pulling up with that much, the sign would be flying upwards. Okay, because there would be twice as much force upwards as there is downwards. So each cable is supporting 1/2 of the weight. So if I write this triangle here for just cable A, okay, I've got this horizontal component, which really isn't important for me. Okay, I've got this 50-degree angle right here, and then this is whatever 1177 divided by 2 is. Okay, so 588.6, okay, is this side of each cable's triangle. All right, and then from there, again, people did things right. They realized this was a trigonometry calculation. They were going to use cosine because they were looking for the hypotenuse. Okay, so all they did was go that the hypotenuse equaled the side they had, the adjacent side, divided by the cos of 50 degrees. Okay, and they calculated the hypotenuse. So they took that number, divided by the cos of 50, and got 915.69 newtons, but we only have two significant figures here. Sorry, we had, no, you could have used the 40 as well. So there's actually, well, that only has two. So if you use this, you have two. If you use the 50, you actually have three. Because it should be 50.0. I divided it by 2. I divided 100, which has three significant figures, by 2. Okay, so it's a weird one. I wouldn't put something like that on the test. It would be ambiguous. Okay, so we are going to say that the tension is 9.2 times 10 to the 2 newtons. Okay, we can't give a direction on that because it's a tension and it's pulling in both directions. Okay, it just asked what's the tension in the cable. It didn't specify whether that was from the building's point of view or the sign or light or whatever it is point of view. Okay, everybody with me there? So again, nothing really difficult mathematically, okay, but we had to see, and it looked like from walking around that most people saw the forces that were involved. There's just this one trick, okay, here that some people missed, okay, which, you know, is minor but still important. All right, questions there? No? All right. We haven't got into inclined planes yet, but we're going to talk about them next. Okay. So the inclined plane is the simplest machine. Right? It allows you to move an object that it allows you to move an object vertically that you would not be able to otherwise lift. Okay? Because there's two ways to get something to a specified height. Lift it there directly or push it up a ramp, which is easier. Pushing it up a ramp, which is less work. Neither. Okay? It takes the same amount of energy to lift something to a specified height as it does to move it up a ramp to a specified height. The difference is the work is easier moving it up the ramp because you use less force over, not time, over a greater distance. Okay, remember, work is force times distance. To lift it requires a big force over a small distance. To push it up a ramp requires a smaller force over a greater distance. That in that way, a ramp is a force multiplier. Okay, I use less force but accomplish the same amount of work. Okay, everyone okay with that? All right. So here's the way that an inclined plane works. You're going to want to copy this one down, maybe title it like inclined planes examples, how to, or something like that. Okay. When we were first talking about forces of vector quantity, I actually drew one of these. Okay, so we're looking at the forces that would be acting on this block if I just set it on this inclined plane. And just to make it as simple as possible, I'm going to say the inclined plane is frictionless as well. So as soon as I set it on there, what's it going to do? It's going to slide down. Okay, what's causing it to slide down? Okay, it's some gravity, not all gravity. Because gravity wants to pull it which way? Straight down. But it's not going to slide straight down. That would be through the ramp. Okay? It's going to slide down the ramp, which is slightly different. So yes, gravity is certainly pulling on this. Okay? It's pulling straight down. Right? So this would be our force of gravity. Since the inclined plane is frictionless, what's the other force acting on the box? Yeah, Tyler's pointing, it's out from the ramp. Yes, it is. What do we call that force? Same one if I set something on a desk, the desk pushes back, we called that? No, normal force, right? We called it normal force. Anytime you set something on something else, you exert a force on something, it exerts a force back. Okay, so there is a normal force and it acts out from the plane. Now, if I'm drawing a free body diagram, I draw that force here. Okay, it acts out from the surface. But if I'm drawing a vector diagram, I draw it here so that my vectors are tail to head. The normal force plus the force of gravity gives me the vector sum of those two forces. And that would be this bottom line, which just happens to be parallel to the plane. That's also the direction that the box is going to move. Oh, it's crazy. Not magic. It's physics. It's better than magic, okay? Because it always works. Always. Unless you screw something up. Okay, so here's the thing we need to realize. That force is what we call F parallel because it's always parallel to the plane. It is the vector sum of normal force and gravity. So this triangle that I've just drawn is always inside of an inclined plane and it's always the same. gravity will always be the hypotenuse. Normal force will always be the adjacent side, and this angle is always the same as the angle the ramp is banked at. Okay, it has to be in order to create a parallel side. They essentially have to be similar triangles. Okay, so it's important to remember how this triangle works. Essentially, it is just finding the vector sum of these two forces. Okay, now, if it's a frictionless incline, that's where it ends. Okay, but what if there is friction? Which way will it go, up or down the ramp? Up the ramp, right? Because the box is going to move down the ramp. Right? So friction would resist. So friction would be up the ramp. Okay. So then I would go, okay, here's my, I've drawn kind of my vector sums, but I've also got this force of friction that's going back, and then my net force would be, okay, right in here. All right. Something like that. Or you might have a question where, okay, and instead of drawing it in here, because it kind of gets confusing, I always just use this, I just use this triangle to get F parallel. Okay. Once I have F parallel, I draw it on here. I say, okay, F parallel is acting down the ramp, and then I put friction up here. Okay, friction's acting up the ramp, and I kind of start over again. Okay, so I only really use that triangle to get the force parallel. So if there was friction, that would be the direction it goes. Now, what if instead of I put it on this ramp and it slides down the ramp, I'm using the ramp to push a box up the ramp? Are there any new forces? I'll repeat myself. I'm pushing the box up the ramp. That's a force, right? Okay. We call that an applied force. So I now have an applied force, which is me pushing up the ramp. F parallel is still down the ramp. Parallel is always down the ramp because it's the sum of normal force and gravity. Where's friction now? It's opposite. I'm moving the box up the ramp, so friction has to act down the ramp. Always remember, friction is always opposing. Okay, so friction would be now here. Okay, and I could find my net force from those forces. All right, so inclined planes still work the same as everything else. Okay, we still have these forces that are in opposition to each other. The only thing that's new is we have to use that little triangle to get the parallel force. Okay, that is the sum of normal force and gravity. Okay. All right, does everyone have this diagram here written out? Because that one's going to be important for you when we start solving inclined plane problems like this one. All right, so I want you to write this one down, and then I'll walk through the solution with you, okay, once you have it written down. Because this one does contain one little trick that we always have to be on the lookout for. All right, so when we have this inclined plane, the first thing we want to do is draw the inclined plane. All right, we know we have a 340 Newton box. Did I give you mass or weight? Weight, which is also the force of gravity. Okay, so what I did is I told you that this side, which is the hypotenuse of that inside triangle, is 340 newtons. All right, so I gave you one of the sides. That means I don't know the mass, but I can find it. Okay, as Tanner was asking earlier, I can just go 340 divided by 9.81, and I'll have the mass, 34.66 kilograms. Okay, you know what, I take that back, you don't need it. But anyway, all right, so now I have this internal triangle here, okay, the one that we talked about before. Okay, we know that the ramp is inclined at 30 degrees. Okay, so we know that this angle inside this triangle is also 30 degrees. This side of the triangle is F parallel. That's the force pulling the box down the ramp. Right? They told us that there's an applied force up the ramp of 200 newtons. And we're looking for the force of friction. So it says the box is being pushed up the ramp. So it is moving up the ramp, which means friction's acting down the ramp. Okay, so now I've identified my important forces. Can I calculate F parallel right now? Because I need it. Okay, how do I do it? It's in a triangle. I have to use trig. Okay, I know the hypotenuse of that triangle is 340. I know the angle in that triangle is 30. Can I find the opposite side? Okay, that's F parallel, right? A ramp is by definition a right angle triangle, yes. Yes, yes, this internal triangle is always a right angle triangle because it's similar. It's a similar triangle to the ramp itself. Okay, all right. So now that I know that, I can calculate F parallel. Okay, F parallel is the opposite side. So I'll go sine of 30 times 340, okay, which will be 170 newtons. Okay, so I know that F parallel is 170 newtons. I know there's 200 newtons of force up the ramp. All right, so I'm missing friction, and that's what the question wants me to calculate. How do I calculate it? I don't know the acceleration. I'm missing a force. I can't do sum of all forces. Or can I? I can. I don't actually have to solve for it, though. It's 0. How do I know F net is 0? It's moving at a constant velocity. Okay? Always be on the lookout for that little tidbit of information in a question. If it tells you constant velocity, it's telling you that the net force is 0, which will help you when it comes time to do the vector sum of all forces. F net in this question equals the applied force plus F parallel, which is the net force of the other two, but okay, it's important. Okay, and then we've got the force of friction. Okay, I'm looking for the force of friction, so I subtract the other two over. So I'll have F net minus the applied force minus the force of friction, minus F parallel, equals the force of friction. All right. Have I still done all the same things I did in any other question? Right? Mass times acceleration gave me 0 because the acceleration was 0. Now I'm doing sum of all forces. So I've got the net force being 0 minus the applied force, 200, minus negative 170, because it's down the ramp, okay, equals force of friction, which is negative 30 newtons, or 30 newtons more accurately, down the ramp. Okay? And that's typically how a inclined plane question will work. Okay, it'll either give you all the forces or the ability to get them and ask for the acceleration, or it'll give you the acceleration and ask you to calculate one of the missing forces. Right? Basically, like any other question, it's just a different context. Now it's a ramp as opposed to a level surface. Okay, so vectors come into play on those. Okay. Start to get an idea of just how many different situations Newton's second law applies to? We're about halfway. I know, it's a lot, okay? But the reason I'm bombarding you with all these different situations is so that as I introduce more and more, you'll need less and less of my help to figure them out. Okay, because you go, okay, I know that this situation applies here. Oh, well, this is a situation like that one, or the last time I had this constant velocity, it meant net force was 0. You're learning all the little tricks, okay, that you can apply to a new and novel situation. All right, this is an inclined plane question, okay? I want you to give it a try. Okay, I'm just going to draw the free body diagram on here so that we're sure we're on the right track. All right, so we have a kid going down a 25-degree hill, which is an inclined plane. Okay, so we know that this angle here is 25 degrees. I'm going to represent the kid with a box. Okay, they are 50 kilograms. All right, we have two forces that are contributing to the movement. Okay, we have F parallel and we have friction, right? That's it. Friction is resisting, F parallel is pulling them down the ramp or down the hill. Okay, so that means we need to calculate F parallel. So don't forget this internal triangle that we always use for that. Okay, I'll give you a few more minutes from there. Okay, so this side is, sorry, that's supposed to be two parallel lines, F parallel. Okay, so guys, just want to illustrate one thing because I had a question about it and just it kind of triggered my memory for this. When I get to the point on this question where I'm calculating net force, okay, What are the only two forces I'm worried about when I calculate the net force acting on the child?
Force of friction, parallel.
Exactly, force of friction and the parallel force. The reason for that is the parallel force is the net force of gravity and normal force. I don't want to put gravity in again. I already took it into account when I calculated F parallel. It's a very common mistake that I see when people are doing an inclined plane problem. They go F parallel plus the force of gravity plus the force of friction plus the normal force. Okay, no. We already took those two forces into account when we calculated this. All right, so we don't factor them in again. We already factored them in when we calculated F parallel. Okay. All right, so now we're at this point here where we got to calculate the force of gravity. So that's going to be 490.5 newtons. Okay, then we're going to calculate F parallel. It's the opposite side. So we'll take our hypotenuse, okay, and we'll multiply it by the sine of 25. Okay, so F parallel is 207.29 newtons. All right, and we know that the force of friction is 150 newtons. So now that I have those, now I can use sum of all forces to get F net. All right, so I got 207.29 minus 150, okay, which is going to give us 57.29 newtons down the ramp as our net force. Sorry, down ramp. Okay, now that I have that, now I can calculate the acceleration of the child, same way we always do, F net divided by mass, so 57.29 down the ramp divided by the mass of the child, which is 50. All right, so we're looking at 1.1, because we only have two significant figures, okay, 1.1 meters per second squared down the ramp. Make sure you include the ramp. If you do not, you are saying it is accelerating through the ramp vertically downwards, which is not correct. Okay. Or in this case, it would be down the hill because this was a kid sledding, but yeah, I wouldn't mark it wrong. Okay. All right, questions on how inclined planes work? Okay, because on that worksheet I gave you yesterday that I had you working on, the last 4 questions are inclined plane questions. You haven't got there yet, but spoiler alert, the last 4 questions are inclined plane questions, and I figured I better go over some in case some of you got there and were working on those, okay, because then you would have gone, Mr. Cooder, I don't know how to do this. Well, now you do. Okay. All right, so I want to finish up, okay, working on not the one from yesterday, okay, but there's actually another worksheet that has some vector problems on it on one side and inclined plane questions on the other side. Okay, so you can see here it says inclined planes worksheet. Every question on there is an inclined plane because inclined planes are great Newton's second law questions. There's always an inclined plane question on the unit exam. There's usually one on the final exam too. So there's a whole sheet on inclined planes. And then there's a forces of vector quantity worksheet. That one's going to involve you probably using a little bit more trig than the other worksheet had you doing. So what I would say is for right now, like go back and forth between the inclined planes worksheet and the forces of vector quantity worksheet. Do question 1 from one of them, then question 1 from the other, and go back and forth. So you're not doing a whole bunch of inclined plane questions in a row. Okay, otherwise it gets kind of monotonous. All right, it gets monotonous anyway, but okay. So you'll need that open on your phone or something like that so you can refer back to it. I'll leave it up here, but I won't be going back and forth between the sheets. Okay. All right, if there's any that give us trouble, then we'll walk through them together, but let's get going on inclined planes and vector quantities.